Creative Math Lecture 25. So again, I remind you, I'd sent out an email and posted this on Blackboard 2 weeks ago. The final exam is Monday, May 20th, 8:30 in the 8:30 to 10:30. We have 5 more lectures. So today, next Monday are on chapter 11. Next Wednesday and the following Monday are on chapter 12. And the last lecture, which is on May 15th, is review for the final. So up to this point, let's say chapters 1 to 10 covered mathematics from the Greeks about 300 BC to the last work and the last mathematician we considered, Euler, in the 18th century. Roughly 736. That was the date for the work we discussed. And now we're going to jump a century because beginning with Euler, mathematics became increasingly rigorous. Now, you might say Greek mathematics was rigorous because they formulated the idea of proven theorem that derived from a small number of axioms and postulates using a small number of methods of inference. One implies another thing. But as mathematics developed, especially through calculus, there was more and more there were more and more ideas that came in that were somewhat nets. So what was less rigorous was the idea of a limit. And calculus, for example, the study limits. So what are the two basic operations in calculus? The derivative and the integral. So if you have a function y equals f of x, say the graph looks like that, you want to some notion of the slope, the rate of increase of the function at a point, or you like to be able to draw the tangent line to the function at a point. And you need, so if this is let's say A, and f of A is equal to B, on the graph, this is the point AB. And we want to draw the tangent to the curve at that point, or we want to approximate the curve by a straight line at that point. And in order to know, so to draw or to compute the tangent line, so this should all be review of semester calculus, to compute the tangent line to the curve y equal f of x at the point f of a, or AB, if we're calling B f a. Now, to draw a line, it suffices to have one point the line goes through, and the tangent line is going to go through this point, and then you need slope of the line. Need slope of the tangent line. And if we call the slope m, the line with slope m passing through a point AB, well, this you're supposed to know from pre-calculus math. what is the equation of the line with the given slope passing through a point? The equation of the line is m equals y equals the slope m, x minus a plus b, right? So this, I hope familiar. This is the point slope formula. The line with slope m passing through the point with coordinates a, b satisfies this equation. And you can see if you let x equal a, y does equal b. And this is, we can also rewrite this mx plus something, and the coefficient of x is the slope. So in order to find the tangent line, you have to find the slope of the tangent line. And the slope, we approximate as follows. So again, this should be just a review of calculus that you know.
Hold on one second. I'm sorry. There appears to be an echo that's coming through the mic somehow. I don't know how that occurred.
I don't know, because the system hasn't changed since the beginning. Yeah. Can you hear me though?
It's a little blurry,
All right,
but
let
I
me
can't.
just
We
look at
can.
one thing, just 1 second. Is there still an echo?
It's fine now.
It's better? Okay, good. So if you have the curve y equals x, I want to find the slope of the tangent, which is some measure of how rapidly the function is increasing at this point. You take a point to the left or to the right of a, say a plus epsilon, and you draw the straight line between these two. So this chord and the slope of the chord. So this point is a f of a, and this point is a plus epsilon, f of a plus epsilon. So the slope of the line joining 2 points, the slope of the chord is the rise from here to here, f of a plus epsilon minus f of a, divided by difference a plus epsilon minus a, which is equal to f of a plus epsilon minus a divided by epsilon. That's the slope of this chord. And of course, that slope depends on the point a plus epsilon. If you had a point over here, you'd have a different slope. And what we do is to define the slope of the chord to be equal to the limit of this ratio as epsilon goes to 0. And when we call that derivative of the function at a, but this is just the limit, the slopes of these chords, the chord from a plus epsilon curve as epsilon goes to 0. So this is the definition of derivative. So this is what you learn at the very beginning of Cal 1. You have limit. Now, question is, what does this mean? Because if you let epsilon equal 0, in the numerator, you get f of a minus f of a is 0. And when epsilon equals 0, the denominator is 0. So if you just plug in epsilon equals 0, you get 0, 0, 0, which doesn't mean anything. So there was a complicated process to understand what does this mean. And in chapter 11 of the text, there's a very nice discussion of this, quoting from Newton and Leibniz and Cauchy. And finally, a definition given by German mathematician Weierstrass, which in the late 19th century, which is still the definition that we use today. So the definition of the limit that is handed down to us from Weierstrass in the 19th century so this is the Weierstrass definition of a limit. We say that if we have a function y equal f of x, to say that limit of the function f of x approaches the number a is equal to L means the following, or if you like. So there's no hand waving in this. This is very precise. For a epsilon greater than 0, there exists a delta greater than 0, such that if you take any x not equal to a, but with delta of a, so x minus a is less than delta and greater than 0. So what is this inequality? To say the absolute value of x minus a, let me just write this a little side. If x minus a is less than delta in absolute value, that's the same as saying x minus a is less than delta and greater than minus delta when you take away the absolute value sign, which is the same as saying x is less than a plus delta and greater than a minus delta. So on the number line, this is a, and this is a plus delta, this is a minus delta, then x is somewhere in the open interval between bigger than a minus delta and smaller than a plus delta, but not equal to a. X minus a is greater than 0. So if x minus a in absolute value is less than delta and greater than 0, that means x is different than a, and x minus a satisfies this inequality. So take out this point, and we can look at any x in either this open interval or this open interval. These are all the real numbers x within distance delta from a. So in the definition of limit, we say the limit of fx equals L means that for every epsilon greater than 0, there's a delta greater than 0, such that if x somewhere in this interval, then the distance from fx to L in absolute value is less than an epsilon. That means that, sorry, f of, yes, this is L, this is L plus epsilon, this is L minus epsilon. It means that somewhere in this interval, from here to here, you have the f of x. So I'm sure, I hope at least, when you took Math 175 or first semester calculus, your instructor explained this to you. It's certainly in every calculus book, but if you forgot or if you've never seen it, this is it. And this is really something that if you're going to be a math major or teach mathematics, you should know. So this is the Weier's definition. It's very precise. So for example, suppose you have the function f of x equal to x squared minus 1 over x minus 1. Let's see, I'm not sure this is a good example.
Who did you say use these notations? Who's the first one?
Sorry?
Who did you say that used this exact notation?
The person who created or introduced it is the mathematician called Weierstrass. And who uses it, it's everyone who's taken calculus in the last 150 years. Right?
So
It's in your calculus book. I mean, and again, I don't know. I mean, you have a freedom of what cover and in what detail, but this is the starting point of calculus. It's the starting point of a lot of the mathematics is the definition of a limit, a precise definition of limit.
so
And the
the
text you'll find this on page 251.
so the echo is back, but I guess there's nothing we can do about that. That's fine. But how is that possible? So it was never incurred in Newton or the other guy, Legwitz, or I forgot his name. They never used these exact notations when they created calculus.
No, so in Newton and Leibniz, which is early 17, well, it's around 17, I don't know, four, I'll make that up, but notion of limit is let's say vague, right? Imprecise, if you like. Certainly imprecise by modern standards. But I also have to point out nothing in Newton, Leibniz is wrong. All the theorems stated are correct. And you might say what used was their intuition of a limit, but their intuition was 100% good. So you can state a theorem and have a proofs not correct, but the theorem may still be true. Everything in Newton and everything in Leibniz is correct. Everything is right. So they had what today we would call an intuitive understanding limit, but didn't have the precise definition, or these they certainly did not have the definition that did not get written down until about 1880 or so. And it's the definition that we use today. And it may be in the future there will be other definition, but there's nothing wrong with this definition. Anything that you prove uses 100% correct. Okay. But beginning the study of limits, careful. Oh, so this I said that the limit is basic in calculus. This is the derivative. Derivative. Where did I define it? Here. This was a definition of a derivative. Here we have a certain function, and we take that as epsilon goes to 0, and that's the derivative of the function at a. So the derivative is a limit. What's the second principal object that we use in calculus? It's the integral. How do you get the integral? So the derivative is the slope of a tangent line at a curve at a point. The integral is, for example, the area under a curve, under the curve that, let's say, y equals f of x, for x between and b. So you have some function. y equals f of x. Let's say it's negative. And we look at the part of the curve from A to B, and we want to find the area on the curve. And this area we call the integral, definite integral. And we use this notation. This is just notation. This is the area under the curve as you go from A to B. That's the definite integral. But what? How do you actually find a number? So one method is to take your interval from A to B, divide it up into subintervals. Suppose we call this x0, so the intervals. So this is x1, this is x2, and so forth. Here you might have xi minus 1, xi. You have each of the subintervals. And the area under the curve is, if I break this area up into n different slices, the area under the curve is the area of each pieces, and you add them up. So if you take, let me just blow this up. Let's say this is xi minus 1, and this is xi, and we want to find out what this area is. So you can approximate the area under the curve by a rectangle. And what rectangle, what does it mean? A rectangle has base, and this is just going to base by a rectangle. The base is the integral from xi minus 1 to xi. This is the base. And I can just pick any number, let me call it xi star in this interval. Take the corresponding point on the curve at that point, draw this horizontal line. So we have a rectangle. And the area of this rectangle is the base times the height. The height, so this is xi star and the value of the function at that point. So that's f of x star, that's the height rectangle. Base is the distance from here to here. Xi minus 1, xi minus 1. Which I'll just call this, so this is f xi star. I'll call this delta xi. So the delta xi is the distance from here to here. I minus xi minus 1 is the base of the rectangle. This is the base of the rectangle. So I can approximate the area of each of the thin slices like this. And so the area on the curve is approximately, if I take some partition, I going from one up to n, I partition the interval up into n pieces. The area of the rectangle at the piece, which is f of xi star times delta xi. Approximately area under the curve. And you would expect, if you take more and more points of subdivision of this initial interval, so you have more and more rectangles, and then you will get a better and better approximation to area. And in the end, the actual area, for which I'm using this notation, this just means the area. You take the limit of the sums, f of xi star delta xi, as these partitions become finer and finer and finer. Delta xi going to 0. So again, in fact, no, in Math 176, they teach you this definition of the interval. First, it's the only definition. That's the definition. and always a departmental final. Math 175 and also Math 176. And then there's always one question where you have to compute this kind of sum. This is called the Riemann. And that's always a problem on the departmental final. So this indeed you have to see. So for the last 100 years at least, when you can you learn calculus and more advanced mathematics, it starts with the limit and the derivative and the integral. They're both limits. This is kind of a quick review of Calc 1 and Calc. Actually, now it's Calc 1 because Calc 1 they introduced the integral near the end of the semester. Any questions about this? This is real fundamental. I mean, like the basic idea of calculus. Some of the basic ideas in calculus. It's important to know and to refresh, to see periodically, to refresh your knowledge of them.
Professor,
Yeah, yes.
is the final exam online or in person?
Final exams in class,
Okay.
not online. Just like our exams, the midterms were.
That's quite unfortunate.
Well, common experience is when you give exams online, that almost everyone gets an A.
I mean,
Right?
I mean, if that's the case, then I don't know what to say.
Yeah. Yes, at some schools in New York now, everything is online. But the way it is. Okay. Now, started to see mathematics in finer detail, and even things like that seem very basic, like real numbers, right? Have like the real number line. There it is. I'm just putting the integer points. There are also other points like that we have. And maybe there it would be square root of 2. And if this 3 and 4, maybe there would be pi. You have all these numbers on the number line. So in some sense, what are the simplest numbers? Well, really the simplest numbers, because this is what you learn when you're a child, positive integers. 1, 2, 3, 4, and so forth. So anthropologists, when they study cultures of people around the world and the history of cultures and language, they're often interested in how different cultures, different peoples understand quantity. And it seems to be the case, this is what you read, that in some cultures, some languages, they don't have words for numbers like 17. They basically have 1, 2, 3, maybe something that is described as any, more than 3, right? And then maybe it's always the case. And then evolved to people who had concept of larger integers. So maybe you get to the positive integers. And then at some point, and this was a very sophisticated concept, you got the idea of 0, right? That's hard. And then even hard were negative numbers, which in some sense were unfamiliar They were certainly not unfamiliar. They were people were uncomfortable with them. So, for example, you saw if you read the text that in the 17th century Italy, when you had a resurgence of mathematics, in particular, we studied Cardano's solution of the cubic equation. We looked at equations of the form x2 plus mx equals where m were positive. And the case was when m and n were not both positive, they would write the equations just differently. So they would only look at positive numbers, just didn't like negative numbers. So it took a while until negative numbers became kind of like mainstream. Though I understand that even today, lots of people like just don't know or can't negative numbers, but if you're a math major, you certainly can. So you have I should say the negative integer. And next, so we have really in some sense the simplest numbers are the integers. And then we looked at ratios of integers. P over Q, which we call fractions or rational numbers. So you have numbers like 5, and then you have numbers like 5 over 13 or 291 over 11 and so forth. So you have an irrational number, an integer you can also think of as 5 over 1. So the integers are rational numbers, but then you have rational numbers. And the thing about rational numbers is that there are lots of them, that the line has covered with them. Right? And in fact, on the number line, again, these small intervals, say from A to B, so A less than B. In any interval between A and B, in every interval from A to B, there are rational numbers. Like you say, any A and any B, in between, there's always a fraction. Right? No matter how close A and B are to each other. And actually, let me pause for a moment and you think about this. Prove this. Right? Prove if A is less than B, there's always a fraction, a rational number between A and B. So let me pause the recording for a second and let you think about it. So any suggestions? Anyone have an idea how to prove that in any small interval on the real line between A and B, always some fraction inside? Let's see. Let me see if I can figure out a way to prove this. Here we have A, and here we have B. And A is less than B, which is the same as saying the length of this interval B minus A is bigger than 0. Now, this is a positive number. Suppose we choose an integer Q so that 1 over Q is less than B minus A, right? So, I mean, because we know that the sequence, right, 1 Q is as Q goes to infinity is 0, right? Because 1, half, a third, fourth, and so forth. These numbers go to 0. So you can always, so if B minus A is bigger than 0, you can always find an integer Q, positive integer, I should say, positive integer Q, where 1 over Q is less than B minus A. So consider the fractions with positive or negative exponents, n over q, n plus 1 over q, n plus 2 over q, and minus 1 over q. Consider all the fractions n over q with denominator q. So here on the number line, you might have some n over q less a, and then n plus 1 over q. This is bigger. How much bigger? It's bigger by 1 over q. And then n plus 2 over q. This is again bigger by 1 over q. If you look at the sequence of fractions n over q, they're getting bigger and bigger and bigger. So at some point, you're going to get past a. So let n be the largest integer, n over q less than or equal to a, right? And these things are getting bigger. At some point, you have to get to a and then go beyond it. So just choose the large integer n, where n over q, or maybe I should call it, I'll call it, say k over q. K over q is less than or equal to a. So we have, let me just blow this up. Here's a, here's b. And here's k over q. And the next biggest number in the sequence of these fractions is k plus 1 over q. And I claim k plus 1 over q is between a and b. So I claim that between a and b, I have k plus 1 over q. K plus 1 over q is bigger than na and less than b. Now, of course, we know k plus 1 over q is bigger than a because k over q is the largest. K over q, k is the large integer, where k over q less than or equal to a. So this means that k plus 1 over q has to be bigger than a. But I also claim that it's less than, right? So I claim k plus 1 over q is strictly less than b. This will be approved by contradiction. Suppose not. That means k plus 1 over q is greater than or equal to b. So we have the following. We have k over q less than or equal to a, less than b, less than or equal to k plus 1 over q. So on the number line, it's like this. Here's a, here's b, here's k over q, here's k plus 1 over q. The distance from b to a is less than b minus a, this minus this. K plus 1 over q minus k over q. But k plus 1 over q minus k over q is 1 over q. But how to choose q? I chose q. So that 1 over q is less than b minus a. Actually, this should be less than or equal. B minus a is less than or equal to plus 1 over q minus a over q. But b minus a was chosen to be bigger than 1 over q. So this says 1 over q strictly less than 1 over q, and that is a constant. So it has to be the case that k plus 1 over q is strict between a and b, which says that between any two numbers, there's always a fraction. Hmm. So that's really a very nice argument. But from that argument, we can say a lot more. This is true for any two real numbers. So suppose we have A and B, and then in between them, there's some fraction somewhere. P1 over Q. We just prove straight between any two numbers, there's a fraction. Well, here's another number and here's a number. So between these two numbers, there's a fraction. And between here and here, there's a number. So there's another fraction. Between and P2 over Q2, these are the two numbers. So then we can there's a fraction. In here, this is going to be a fraction. And here and here. And so, and we continue this, and what we're led to is the following variant statement, which says, between every two real numbers, A less than B, there are infinitely many fractions. Because you just keep subdividing this interval, you pick a fraction that creates two new intervals. In those two intervals are two more fractions, and just keep going on forever and ever. So between every two real numbers, A less than B, there are infinitely many different fractions. Really different. Reduce the lowest terms, whatever you want to call it. We know not every number is a fraction. Or another for a fraction is a rational number, right? We know irrational numbers exist. For example, square root 2 is irrational. And one of the things we learned early on was a proof that the square root of is a fraction. It's also true that between every two real numbers, A less than B, there are infinitely many irrational numbers. And one simple proof of this statement is the following. So here's simple proof. Suppose A is less than B. Then square root of 2 is positive. So A over the square root of 2 is less than B over the square root of 2. So these are two real numbers again. That A over root 2 and B over root 2, in between them, there has to be a fraction. So there's some P over Q between A over root 2 and B over root 2, which means A is less multiplied by the square root of 2. P of 2 square root of 2 is less than B. So between A and B, there's always a rational multiple of the square root of 2. And this number is rational. Because if this were rational, square root of 2 would be rational. And you have infinitely many fractions P over Q that satisfy this inequality. So there are infinitely many fractions P over Q that satisfy this equality, which means that there are infinitely rational numbers between A and B. So that's a proof of the state. Now, how many rational numbers are there? There are infinitely many, of course. How many rational numbers are there? Also infinitely many. I mean, for one thing, p over q times root 2 is always irrational. So for every rational over q, the irrational p over root 2. So you can say there are infinitely many. This is my shorthand. This is infinitely many rational numbers. There are also infinitely many rational numbers. So an obvious conclusion is the number of rational numbers is infinite equals the number of irrational numbers. Right? Because you have infinitely many of both. So what is going to be the great theorem in this chapter, though I'm not going to prove it until Monday, is that this statement is wrong. You may have many rationals and many irrationals, but you have the same number of E. And the reason it's wrong is we need a better understanding of infinity. Now, this could lead you in different directions. One is the mathematical direction. Of course, it could lead you into some, mystical philosophies or religions or, methods of some improvement. What does it mean to understand infinity? I don't know, make you religious perhaps, but we're interested in a very much more understanding of infinity from the point of view of mathematics, where we want to know in what sense, and maybe this is ridiculous, but in what sense could you possibly say that if you have infinitely many rationals and infinitely many irrationals, that you don't have the same number of rationals, irrationals, right? So you want to get a better understanding of infinity. Let's look at a simple example. We have the positive integers. 1, 2, 3, 4, 5, 6, and so forth. And we have the even positive integers. 2, 4, 8, 10, and so forth. All right. Now, do you have more positive integers or more even positive integers? So one of view is both sets are infinite. So you have the same number of elements in each of these sets. Alternatively, you could say there are twice any integers as positive integers as even integers. Here, integers means positive, as even positive integers, right? Because like up to 10, you have 5 even integers, but 10 integers. So twice as many integers, even integers, so there are more elements in the integers than in the even integers, right? So which is it? Would you say they're more integers than even integers, or the same number? Because both sets are infinite, but they're obviously numbers in the first set, second. The first set of integers contains all the odds, right? Huh. Any thoughts on this vote? Who to say they have the same, the two sets have the same number of elements? Who wants to say that they don't have the number of elements? They're more integers than even integers.
Well, don't they just alternate? So, I mean, based on that, it would be even.
Sorry. So, which set has more than the other, or do they have the same number?
The same.
And why are you saying that?
Because they alternate, so depending
When
on
you say alternate, what do you mean by alternate?
from odd to even.
Yeah.
So as you increase, they alternate, so it will be the same depending on where you decide to end.
So isn't that the same thing? Both sets are infinite. So you take the first 10 elements in the first set, and there are going to be 10 elements in the second set, or
But since you end on, so if you go by infinite, they should be even.
by even mean equal.
Yeah, equal.
Yeah. Yeah, you don't want to say even, because we're also using even for even integer, but you mean in equal. Okay.
Yeah, they would be equal to each other. But if you end on a even number, then they should be more even than odd.
What do you mean by an even number?
So like you see how you went from positive integers from 1 to 10?
Yeah.
If you end on an even number, you should have more evens than odds, I think.
Well, if you end at 10, if you look at all the numbers from 1 to 10, you have 5 even and 5 odd. Right? If you end on an odd number, you'll have one more or odd. Like if you end on 9, you'll have 4 evens, 2, 4, 6, and 5 odds. 1 through 5, 7, and 9. That's true, but of course you don't want to end at any point, because these are infinite sets. You kind of want to go on forever. Right? I mean, I guess the only point I'm trying to make is it's an interesting question to think about, right? And the first person who seems to have thought of this serious way was a mathematician in the late 19th century named Georg Cantor. He actually looked at this from a religious point of view. He actually did write stuff about religion as well as about these numbers, and the author of the conjectures that in his immediate family there were Protestants, Catholics, and Jews, so he was like surrounded by different religious points of view. But it was Cantor who first came up with a precise note. Just the way Weierstrass was the first person to come up with a precise definition of a limit. So Cantor, he defined what it means for two sets to have the same number of elements. right? What do you mean for two sets to have the same number of elements? Of course, if you have finite sets, 1, 2, and 3, and 7 minus 35, 9,000, you could say that these two sets they each have 3 elements, so of course they have the same number of elements. So finite sets, it's sort of an easy question. I put easy in quotation marks, but this set has 3 elements, this set has 3 elements. And actually, we say that the cardinality, this is just a syntactical word for this. Cardinality of a set is number of elements it contains. The cardinality of a set S, and it's denoted sometimes by S and absolute signs. So if I take the set at 1, 2, 3, the number of elements in that set is 3. And if I take this 7 minus 35, 9,000, the number of elements in this set is 3. So these sets, the same number of elements or the same cardinality. Right. But we want a notion of equality number of elements that applies to infinite sets as well as finite sets. And this is really a very, in retrospect, you might say, well, obvious definition, but it really wasn't obvious. It took some degree of genius or brilliance to understand the concept of cardinality size of a set, or sometimes the old language was equivalent. So 2 sets are equivalent. Well, this was Cantor's definition. And let me just write it down. This is again, if you're looking at text, the bottom of page 253. 2 sets, M and N, are equivalent if it is possible to put them by some law, whatever that means, by some law, in such a relation to one another that every element of each one of them there corresponds one and an old one element of the other. So what does that mean? Let me go back to this example. I had the set 1, 2, 3, and the 7 minus 35, 99. So let's say to the element 1, there corresponds 7. To the element 2 corresponds minus 35. To the element 3, there corresponds element 9,000. So to every element of this set, there corresponds one and only one element of the other. And converse. So 7 corresponds to 2. Minus 35 corresponds to 2. 3 to 2. 7 corresponds to 1. Minus 35 to 2. And 9,003. So these two sets are equivalent, or in slightly different, more modern language. they have the same cardinality or the same number of elements. And another way to express this is following. We just do it in more modern words. Sets X and Y are equivalent or have the same size or have the same cardinality if there is a one-to-one, let's say there is a function f from x to y that is one-to-one and onto. This is sometimes called a one-to-one correspondence. And what that means is you have a function from x to y. So one means the following. If f of x is equal to y and f of x prime is equal to y, that only can happen if x equals x prime. So this is the set x, this is the set y. If I have an element x that gets mapped to y, and another element in prime that gets mapped to this y, the only way they can happen is if this is the same element. You have two different elements that can map to the same thing. That's what it means for a function to be one-to-one. And a function is onto means for every y, there exists an x in x with f of x equal to. For every y, some element in x, they map to y. So Cantor's definition of sets having the same number of elements is that there's one-to-one correspondence between the sets. So this, for example, suppose I take positive integers. Let me take the even integers. So to define a function f from the positive integers to the even integers by very simple definition, f of x is 2x. So by this definition, f of 1 is 2. F of 2 is 4. F of 3 is 6. F of 4 is 8, and so on. Now if you two different numbers, a and b, or x, yeah, a and b, then if a is different from b, 2a is different from 2b. So this function is one-to-one. And if I take even integer 2n, the number n gets mapped up to 2n. So this function is one-to-one and onto. So by Cantor's definition, of course, I have one-to-one correspondence between the even integers, between the integers and even integers. These two sets, they're both infinite, but they have the same number of elements. Okay. So this is really a flat definition. I mean, it's 100% certain that I'm going to ask you something like on the final exam. It's like, again, one of the basic foundations for mathematics, this notion of the formal definition of what it means for two to have the same number of elements. Well, what about other finite sets? Suppose we take the set of all integers. 3 minus 2 minus 1 0 1 2 and so forth. Does this have the same number of elements as the positive integers? Well, it does if there's a one-to-one correspondence between the sets. So then we should have show you a one-to-one correspondence. And then I'll try to find a way to write it down with a formula, but you don't need a formula, you just need one-to-one correspondence. So here I have the positive integers, 1, 2, 3, 4, 5, and so forth. And here I have the integers. I'll write them down like 0, 1, minus 1, 2, minus 2, 3 minus 3, 4 minus 4, and so forth. So correspondence is going to send the number 1 to 0, number 2 to 1, 3 to minus 1, 4 to 2, 5 to minus 2, 6 to 3, 7, and it's pretty clear. Keep on doing this. This is a one-to-one correspondence between the positive integers and of all the integers. Let's see. What's the formula for this? Well, let's try to find a function f from n to z that gives this one-to-one correspondence. Well, even integers is easy because if n is even, you can let f of n be equal to n over 2, right? So 2 goes to 1, 4 goes to 2, 6 goes to 3, 8 goes to 4, and so forth. Right? What about if n odd? Let's see, for n odd, this is trickier. Let's see, 5 goes to minus 1, 3 goes to minus 1, 5 goes to 2 minus 2. So it looks like if you had the number 2k plus 1, an odd number, if you suppose n is 2k plus 1, then n minus 1 would be 2k. So n minus 1 over 2 would be k. And so minus n minus 1 over 2 would be minus e. Let's see if it works. So suppose for n odd, we define f of n to, and see what is minus n minus 1 over 2. That's just 1 minus n over 2. So let's look at, so f of 1 is 1 minus 1 over 2 is 0 over 2 is 0. That's this. F of 3 is 1 minus 3 over 2, which is minus 2 over 2, which is minus 1. That's this. F of 5 is 1 minus 5 over 2. Is minus 4 over 2. Is minus 2. That's this. F of 7 is 1 minus 7 over 2, which is minus 6 over 2, is minus 3. It looks like this is going to work. N is 2k plus 1. F of n, which is f of 2k plus 1, is 1 minus 2k plus 1 over 2, is 1 minus 2k minus 1. You have minus 2k over 2 or minus k. So as k goes 0, 1, 2, 1, 2, 3, 4, this gives you all the numbers. So I could justify my function like this. Here's a one-to-one correspondence between these two sets. F of n is equal to n over 2 if n is even, and 1 minus n over 2 if n is odd. And there's a one-to-one correspondence between these two sets. So the integer and the even integers, sorry, the integers and the odd and all the positive integers have the same number of elements. Huh. Actually, Cantor just wanted to have a symbol for the number of integers, or the number of integers. So the cardinality, the set n of positive integers is denoted by this symbol, which is denoted red olive 0. So this is the Hebrew letter olive, first letter in the Hebrew alphabet. So the Greek letter alpha was already used a lot. So for whatever reason, Cantor chose the Hebrew letter Aleph sub-0 to the cardinality of the even integers. We have the cardinality of the set of even integers is 0. But we already see the number of even integers is the number of positive integers. The number of all integers is equal to the cardinality of positive integers. So all of these sets have cardinality of 0. In the text, they use this slightly different donation. So the text writes, instead of the cardinality of a set as the set with absolute value signs around it, they put a bar over. So this is notation that's just a text, but this is the standard notation. Okay, so even integers and odd integers, positive integers and all integers, they have the same number of elements. Suppose we consider the rational numbers. Q. It's the set of all rational numbers. P over Q, all fractions. How many fractions are? Well, it turns out, so it looks like there are a lot more fractions than there are integers, right? Because a lot more. But Cantor proved, so that this is in a sense surprising, Cantor proved that the cardinality of the set of rational numbers is also Aleph of naught. So there exists a 1-1 correspondence between Z and Q. So there are different ways to it, and I don't, my favorite way, not the one in the text, but since you have the text, I'll describe in the text. So suppose I make some giant picture. I list all of the rational numbers, positive, negative, 0. So let me start with all the functions. Actually, take a new piece of paper for this. Suppose I take all the fractions where the numerator is 1, and the denominator is always going to be positive. 1, a half, a third, a fourth, a fifth, a sixth, and so forth. So this column of all the fractions with numerator 1. And then I have all fractions with numerator -1. -1, minus a half, minus a third, minus fourth, minus a fifth, minus a sixth, and so forth. And then I make a column with all the fractions with numerator 2, except from now on, I only write down the fractions that have been reduced to lowest term. So I have 2, 2 over 2 is 1, 2/3, 2/4 is a half, I don't need that, 2/5, 2/6 is a third, 2/7, 2/9, 2 over that. So these are all the fractions. The denominator is always positive, and here the numerator is 2 reduced to lowest terms. And -2, minus 2/3, minus 2/5, minus 2/6, and so forth. And then 3 halves, not 3 over 3, because that's 1, 3/4, 3/5, not 3 over 6, because that's 2, 3/7, 3/8, and so forth. Then all the fractions with denominator -3. No, numerator -3, minus 3, minus 3 halves, minus 3/4, minus 3/5, minus 3/7, and then 4 and minus 4 and so forth. So every positive integer q, they're all fractions with every positive integer p. They're all fractions with numerator p, and all the fractions with numerator minus p, and so forth. And what we've written down here, oh, and then I shouldn't forget 0, 0, 0. So here's 0, and then you hold the non-zero fractions in this infinite array. So what I've written down is all fractions, or all rational numbers. And I claim there's a one-one correspondence between these numbers and positive integers. So I claim the cardinality of Q is the same as the cardinality of the set of positive integers. So I'm going to describe a one-to-one correspondence F from a Q. So 1 is going to be mapped to 0, right? And I have the positive integers. I have to say where each integer is incidental. 2 gets into 1. And actually, what I'm going to look at is in this array, I'm not going to go across column. I'm not going to cross rows or column. I'm actually going to go diagonals. So 3 will get sent to this number, and 4 will get sent to this. And then on this diagonal, 5 will get sent to 6 here and 7 here. And on this diagonal, 8 gets sent -2, 9 gets sent to this, 10 gets sent to 11 gets sent. As I go down these diagonals, I can enumerate fractions. The first, the second, third, fourth. Let me actually emphasize diagonals. first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 18th, and so forth. And you can see matching up 1 to 1 every positive integer with a fraction. Every fraction eventually gets, because no matter where it is, every fraction is on some diagonal. Eventually, I'll be going down that diagonal. So this is 1-to-1 correspondence between the rational numbers, positive integers. And so we have these sets have a number of elements. We have the even integers. They're contained in the positive integers. They're contained in the set of all the integers. They're contained in the set of rationals. And these four all have cardinality. Aleph naught. So let's see, what's the next larger obvious set to consider? We have the rational number, and that's considered inside the real numbers. So we can ask, does the cardinality of the rational numbers also equal Aleph naught? Right? And the great theorem in this chapter says no. The answer to this question is no. The cardinality of the real numbers is not Aleph naught. In fact, if we just take the interval from 0 to 1, so this interval 0 to 1, which is all real numbers x, which are strictly between 0 and 1, is not. Now, if a set is cardinality Aleph naught, we say it's countable, or count infinite, is not, or the word that denumerable. That's the word that the text is using. Is not denumerable, means not equal to Aleph naught. So we have two infinite sets. The positive integers and the real numbers. And they have different sizes. Different cardinalities. So this means, in some sense, that there are different infinities. Right? Some infinite numbers are different from other infinite numbers. Infinite number just means some sets that are infinite have more elements than some other infinite set. And this was a truly revolutionary idea. That you can't just say two sets of the same number of elements if they're both infinite. Some infinite sets with this very strict definition and very natural definition in retrospect of the means for two sets of the same number of elements. We have two infinite sets with different numbers of elements. So in fact, you can have arithmetic of infinity. You can, it's a whole huge subject, and it's called set theory. And this is a great theorem I'll prove on Monday. And because this is a new concept for all, or certainly most of you, I would certainly encourage you to study chapter 11 before Monday, so you have some idea of what it is that we're going to be talking about before we talk about it. That always helps. Even to understand what you read, it gives you some background for what we're going to be doing on Monday. But this is the theorem for that the infinite set of real numbers has strictly more elements in this very precise mathematical definition than the set of integers. So a set that has Aleph not elements is called denumerable. That means you can like write them as a sequence of numbers. The real numbers are enumerable. That's a real big deal. Okay. All right. Well, we covered a lot today, and this is really new, which is nice to study something new that you might not have seen before. And we will continue this on Monday. Again, certainly tonight and tomorrow at 7, I have online sessions. So if you have a question about this or anything else that we've been doing, I encourage you to go on and ask questions. Anything else for today?
Real quick, what
Yes.
was the notation for all rational numbers? Is that a
Q.
oh, it's Q, okay.
Yeah. The rational numbers are Q. Okay. This is the standard notation for the rational numbers. It may not be used in the text. They might just use the words, thus set of rational numbers, but it's denoted by Q. It's kind of bold for Q. Anything else? Not? It's going to be a beautiful day, so you have a chance to enjoy it. And see you next lecture next Monday. Oh, and happy May Day. Bye.